Hello everyone, how are you all doing? Welcome to IGBits. We train, you learn. Today we shall continue our topic work per energy. We will see some more sums. Alright, without further delay, let's get started. We have our YouTube channel. Visit us at IGBits in YouTube. Please feel free to subscribe and click on bell icon to get the notifications. Your support is very important for us to work together to share many more knowledge sessions across. Okay. Thank you all who are actually being with us and supporting us. This is a great platform that we are aiming for. Thank you all once again. Today we shall see potential energy of a spring. We studied potential energy definition, right? The energy of a body by virtue of its position, configuration, or state of strength is nothing but your potential energy. But what about the potential energy with respect to spring? Whenever an elastic body, right, precisely in our case is a spring, is either stretched or compressed. So work is being done against, elastic spring force is what we can call it as a potential energy, precisely. So elastic potential energy is equal to work done to stretch the spring, which is depends upon two parameters, a spring constant and the distance stretched. So I'm sure I think we know Hooke's law, right? Based on the Hooke's law, what we say about is F is directly proportional to minus X. F means like a spring force, X is the displacement. In case of applying a force to extend the string, so spring extension. In this case, a force is directly proportional to your X, but the spring force is opposite direction Fs. We are here considering a spring force, right? A spring force is basically elastic potential energy because it stores the potential energy. So the force is directly proportional to your displacement is what we consider here. And hence Fs equal to minus K into X. K means a spring constant. A spring constant value K would vary. Large if the spring is a stiff one, and then K value would be a small if spring is soft. But anyway, you will get, given that value in your problem statement, so you should be able to solve it. So now our case would be F can be a constant value, F can be a variable value. Precisely in the spring forces, the forces is like a variable forces, which means a conservative force, right? And hence, if at all you need to find out a work done equal to F dot S, is it? So if it's a fixed case, F and S you can dot product or multiply, you will get it. What if it is a variable force? If it is a variable force, then your work done would be integration of F into ds. Right? Ds means like dx. Certain limit of like initial to the final, arbitrary value, final value. Right? So F means like minus kx. So you have to put like a minus kx into dx. Right? So if you integrate this one, minus k constant you can take out. X would be x squared by 2 because integration of x dx would be x to the power of 1 plus 1 by 1 plus 1. So x squared by 2. Right? So that's why I made it like minus x squared by 2. So f k x squared would be your work done in case of a variable force. Right? These formulas are very important. What we are also saying here is change in potential energy is also nothing but your work done. So your potential energy would be directly depending upon x square or k. These are the two special cases that you have to understand. There are the instances where if the x is doubled, what would be the potential energy? Potential energy would be square of the displacement, right? That is a the kind of energy that you are going to store in the spring by displacing the position from the reference to some arbitrary distance. Clear? Let's look at the case conservation of mechanical energy. Conservation of mechanical energy. Any one of you can help me? What would be the kinetic energy of initial plus potential energy of initial equal to kinetic energy of final plus potential energy of final, right? This is a conservation of mechanical energy. So let's put the formula F m vi square plus F k xi square in case of a spring equal to half m v final square plus F k x final square, right? So let's move them. F m vf square minus F m vi square equal to minus half k x f square minus of half k xi square, isn't it? So this is called a change in kinetic energy, correct? So this is change in kinetic energy equal to change in potential energy. So also nothing but your work done. Work energy theorem talks about, right? So we are talking about potential energy case where we have work done equal to negative du. So this is a point that we have to remember at this case. Any doubt? So conservative work done in case of a spring. Change in potential energy is equal to negative work done. A statement. Change in potential energy is equal to negative work done. We studied a spring force is called a reference force. We also talk about change in potential energy is nothing but your work done. So what we studied in the previous slide, du equal to negative energy, negative work done, right? So du means what? Potential energy of final minus potential energy of initial equal to your work done. We can represent this one integration of minus kx dx, right? So at xf would be any arbitrary position x. Initial value is a reference. Let's take a reference position. Reference position means x equal to 0. At x equal to 0, your potential energy would be 0, and hence I will neglect this one. What I say, like, this arbitrary value, at arbitrary x position, my potential energy bu equal to, so this is kx dx, isn't it? Right. So there should be some limits. The limits would be the initial value x0 to some arbitrary value x to x0, right? So how do you define now? K into x square by 2, isn't kx square by 2 of apply x0 to some arbitrary value. How do you extend this one? You have to put k x square by 2 minus k0 square by 2. So this is gone. So ux, potential energy at arbitrary displacement x, equal to half k x square. So you can also say half kx square is nothing but your work done. This is also nothing but your potential energy. Are you clear? So we spoke about a general definition, and we spoke about like a spring, a reference position, and then a spring extension, spring compression, and then we take an example of extension case and then applied. Work energy theory you applied, and conservation of mechanical energy also we studied. So we understand the work done relationship between the work done, kinetic energy, change in kinetic energy, change in potential energy, and then and the work done, how both are related, and then how work done equal to minus half kx square is also nothing but your a potential energy, right? So the finally half kx square equal to ux minus half kx square equal to minus work done. So potential energy, change in potential energy, nothing but work done in the negative direction, right? We talk about a change in potential energy, not the potential energy. Make a point, right? At infinite point, the potential energy is considered as a zero. From there, we are bringing the the work done for bringing a some the mass from infinite point to the finite point. Then what is the displacement? That sort of the discussion that we can do with the potential energy. Power. What is meant by power? Power is defined as a rate of doing work. So we have a work, and then we are trying to relate between the work done by the time is nothing but your average power or the power. Power is a scalar quantity, right? If you have a if you look at a instantaneous power, means like P instantaneous is nothing but dW by dt. dW work done, change in work done is nothing but F dot ds, right? So F dot ds by dt is what your P instantaneous value. ds by dt is nothing but your V, right? Change in displacement by change in time is called V, velocity. So P instants is equal your force into velocity. This is one more definition you have to understand. P instant equal to force and velocity vectors. So W by T or F into V we can consider for solving the problems. The other way, the power is also defined as a rate of change of kinetic energy per unit time, because work done by time. So rate of change of kinetic energy by time is called your power. So dk by dt can also be considered as your power. So three ways you can define. Based off a scenario, you should be able to solve the you know problems related to power. I hope this helps. Thanks for watching. Please like, share, subscribe, click on bell icon, and leave the comments. Logically, we reached end of the session today. We shall continue remaining in tomorrow's class. Thank you all who are joined and participated actively in today's class. See you all tomorrow. Stay tuned to next session. Thank you. Have a good day. Bye bye.